Alright, good morning. Today we're going to talk about section 7.3, simplifying and combining radical expressions. So I've noticed, you may have noticed several times I talked about the word radical versus root. The book uses the more formal term radical, and I suppose that's okay. I prefer the more descriptive root word. Let me show you why. For example, if I start out with the number 2, and if I put that 2 into the x squared machine, I come out in my range with a value of 4. Now, if I want to find out if I basically want to reverse the process or invert the process, I want to find out where 4 came from under this x squared operation. In other words, I want to find where 4 was rooted in, working that operation in reverse. So I prefer the term square root rather than radical. I put 4 into the square root of x machine, and I come back to 2, and I find where the root of 4 was under the x squared operation. Okay? So root radical is kind of all the same. Radical is the more formal term. Alright, we want to talk about simplifying radical expressions. And some of these can be kind of nasty, but they can be tamed if we smartly invoke some well-known rules. Well, let me illustrate kind of a silly example. It may appear silly at first. The square root of 100 is 10, is it not? We all know that. 10 is the number I square to get 100. Well, I can break up 100 under that root sign as 4 times 25, can we not? Right? Now notice, we haven't proven this, but I'm going to motivate your understanding by proving this is true. I claim I can break up a root sign over a product. In some ways, a root is an exponent, a fractional exponent if you will, and I can distribute exponents over products. The square root of 4 is 2, the square root of 25 is 5, and of course 2 times 5 equals 10. So I can arrive at the same answer by breaking up that radicand really any way I like, and that leads to a more general property. In general, I claim this: the nth root of a product is the product of the individual nth roots. And we're going to use that to our advantage to simplify some pretty nasty root expressions. Alright, so in general we'll invoke this rule to simplify some things. For example, let's start out nice and easy. Simplify the square root of 12. Well, the first thing I would do is look for perfect squares. 12 is not a perfect square, but it does contain factors that are perfect squares. Well, let me write perfect squares. Perfect squares are squares of integers. 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, 4 squared equals 16, and we're too big. 12 is certainly not on this list, okay, of perfect square integers. Well, so 12 isn't going to come out from under that root sign cleanly, but I can break it up as 4 times 3. 12 equals 4 times 3, so the square root of 12 equals really the square root of 4 times the square root of 3, and of course the square root of 4 I can claim is 2, and my final answer, 2 times square root of 3, I think our author and most students would write a final answer for this simplification problem is 2 root 3, with an implied multiplication between 2 and the square root of 3. Okay, 2 square root of 12 is simplified to 2 root 3. Alright, the book's got a fancy definition of what simplified radical form or simplified root form is. Basically, you get everything out from under that root sign that you can. Get everything possible out from under the root sign, or the radical sign, root sign. Okay, of course I'm being informal here, but I think we all get the idea. Example, simplify. The square root of 98. Well, 1 squared is 1, 2 squared is 4, 3 squared is 9, and up the list. I think you'll agree that 98 is not going to be on this list. 98 is not a perfect square. So I can't take it out totally from under that root sign, but what I can do is say 98 is 49 times 2. And 49 is a perfect square. Right? So I can break this up as the square root of 49 times the square root of 2. And the square root of 49 is 7. And of course my final answer here would be 7 root 2. Simplified root form, get everything out from under that root sign that you can. So here I was looking for the biggest square factor that was biggest square that was a factor of 98. Simplifying. The cube root of 54. This process works for higher order roots as well. Cube roots, fourth roots, fifth roots, of which we'll see today. Well, if we're looking for cube roots, we're looking for perfect third powers. Let's see, 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. We're too big already. 54 is not going to be on this list of perfect third powers. So I can't take 54 totally out from under that root sign, but 54 does contain a factor of 27, does it not? 54 is 27 times 2, and I can break up that root sign to my advantage, get everything out from under that root sign that I can. The cube root of 27 is of course 3, so my final answer here would be 3 times the third root of 2. Now be careful, be sure to indicate the index of that root here. When no index is specified, we assume it's a square root, so if you leave out the index, it's a wrong response. 3 times the third root of 2. Okay? Another one. Simplify. Minus the fourth root of 48. So here I'm going to be looking for perfect fourth powers. Well, we may not be so familiar with fourth powers. 1 to any power is 1. 2 to the fourth power is 16. 3 to the fourth power is 81. Too big. So 48 is not on the list, but it does contain a factor of 16 that is on the list. Watch this. I'll do minus the fourth root of 16 times 3. 48 is 16 times 3, is it not? Alright, 16 is on this list of perfect fourth powers. Again, the negative sign stays outside. The fourth root of 16 is 2 times the fourth root of 3 has to stay inside. Please remember to specify that index in your final answer. Minus 2, 4 roots, or the fourth root of 3. Minus 2 times the fourth root of 3. Alright, the same game that we played with simplifying numerical root expressions, we can play with variable root expressions. Show you what I mean here. Simplify. In other words, return your answer in simplified root form or simplify radical form. Well, the square root of m to the ninth. Well, m to the ninth is not a perfect square. There is no single quantity that I can square to get m to the ninth because my exponent is odd and my index is even. Well, what I can do is break it up thusly. Right? M to the ninth can be written as m to the eighth times m, can it not? And m to the eighth is a perfect square. Remember, m to the fourth squared is m to the eighth, so I can claim the square root of m to the eighth is m to the fourth times the remaining factor of m that stays inside, m to the fourth times the square root of m to the first power. And we usually don't write an index of 2. The assumption is if no index is specified, we assume second root or square root. Alright? The long and short of it is I can take out as many powers of your variable that are multiples of your index. That's a nice little hint. Right? You can take out as many powers of your variable from under a root sign that are multiples of your index. Let me get a fresh screen. We'll do some more examples. Simplify, or in other words, write your answer in simplified radical form. The square root of 128 times a to the 5th power. Again, my index is an implied 2. 128 is not a perfect square. A to the 5th is not a perfect square. But they both contain factors that are perfect squares. What I'm going to do is pile up by commutativity and associativity of multiplication, I can pile up the perfect square factors that are going to come out from under that root sign. 128 is not a perfect square, but 64 is, and 64 is a factor of 128. A to the 5th is not a perfect square, but it contains 4 powers of a that is a perfect square. Well, that'll leave one factor of a or one power of a under that root sign. Alright, breaking things up. Well, I suppose we don't need to be so formal after we've practiced these a few times. The square root of 64 a to the 4th, of course, is 8a squared, no absolute value symbol needed, times the square root. Oops, I've made a mistake. Oh, maybe it's good I made a mistake. This could happen to you. Let me go back. I forgot 64 times 2 is 128, so please make that correction. Let me erase all this. Please forgive me. Let me check. 128 is 64 times 2, is it not? And a to the 5th is a to the 4th times a. Alright, looks good. So I made the proper correction. Let me go ahead and painstakingly draw this out now. Alright, so I can break up a root over a product any way I like. Work that to my advantage here. The square root of 64 is 8. The square root of a to the 4th is a squared times the square root of 2a. Not a, but 2a. 2a has to stay inside, okay? Simplified root form. Alright. A few more examples to go. Simplify. Let's try it with third roots, cube roots. Alright, simplify to express something in simplified root form means you get everything out from under that root sign that you can. Well, 24 is not a perfect third power, but it contains a factor of -8 that is. So let me break up minus 24 as minus 8 times 3. Is it not? Alright. And x to the 5th power contains 3 factors of x that it can come out, and 2 will have to stay inside. Alright, let me check this. Minus 24 is minus 8 times 3. X to the 5th is x cubed times x squared. Alright, so the stuff I've piled up here is going to come out. The cube root of minus 8 is -2. The cube root of x cubed is just x, and those remaining factors, I call them residue factors, has to stay inside. So I'll get minus 2x times the cube root of 3x squared as the final answer. Okay? Simplify. And let's talk about some fourth roots. the fourth root of t to the 8th times u to the 15th power. Well, 1 is my numerical coefficient inside that root sign, and the fourth root of 1 is 1. So what I'm going to deal with is these powers of variables. Remember we said before, you can take out as many powers of your variable that are multiples of your index. My index is 4. 8 is a multiple of 4, so all those powers of t are going to come out. Some of these u's have to stay inside. Well, the largest power that's a multiple of 4 is going to be 12. That's less than 15. So u to the 12th will come out, and 3 factors of u, 3 powers of u are going to have to stay inside. Okay? Alright, I'll break up my root sign. Being nice and formal about it. Alright. The fourth root of t to the 8th power is t squared. Please convince yourself t squared is the quantity I raised to the 4th power to get t to the 8th. Similarly, the fourth root of u to the 12th power is u cubed. Some people take the little memory device, take your exponent and divide by your index. 12 over 4 is 3. Nice little hint in performing this operation. Times the fourth root of u cubed. Please be sure to specify your index if it's not 2. So there's my final answer, t squared u cubed times the fourth root of u cubed. Okay? Simplify or express in simplified root form. I've got the cube root of 189 c to the 4th d cubed. I believe this is on your homework list. Well, I'm looking for perfect third powers. 189, as these numbers get bigger, they may or may not look familiar to you. Let me save you some looking. 189 does have a factor of 27 buried in it. 27 times 7 is 189. Well, the long and short of it is 27 can come out, and a 7, or a factor of 7, is going to stay inside. So I'll rewrite this radicand as the cube root of 27 times, well, 3 powers of c can come out, 3 powers of d can come out. What stays inside? Well, 1 factor of 7, and of course 1 factor of c. Alright, so these are perfect third power factors that can come out. The cube root of 27 is 3, the cube root of c cubed is c, the cube root of d cubed is d. What stays inside? Times the cube root of 7c. Here's my final answer there. Alright, 2 more, I promise. Simplify. I believe both of these are on the homework list also. The fourth root of 208 m to the 4th n. Alright, 208, I had to stare at this one for a while. 208, well, it's not a perfect 4th power. I'll save you looking, but I can break it up as 16 times 3, and 16 is a perfect 4th power. Remember, we're looking for 4th powers that I can take out from under that root sign. Alright, so let me rewrite this radicand now. I'll take the fourth root of 208, the fourth root, I'll call it 16, can come out. M to the 4th can come out, all 4 powers of m, times, well, what remains inside, of course, is going to be a factor of 13 and a factor of n. Alright, the fourth root of 16, of course, is 2, as we know from last section. The fourth root of m to the 4th, that's just m. Technically, it should be the absolute value of m, should it not? So, let me put that in the answer. Times the fourth root of 13n. Alright, sometimes our book gets around the absolute value symbols by statements like this. they'll say assume variables represent positive quantities. I'll just say positives. And if that's a restriction in the problem set, I can then do away with the absolute value symbols and say my answer is 2m times the fourth root of 13n with that restriction. Alright, one more. Simplify. The fifth root of 243 times r to the 22nd power. Alright, I'm looking for perfect fifth powers, and let's see, I think I see it. Let's see, what's 3 to the fifth power is 3 times 3 times 3 times 3 times 3, of course. 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. Yes, 243 is 3 to the fifth power. So I can take out all of this coefficient, and again, you can take out as many powers of your variable here that are multiples of your index. And the largest multiple of 5 that's less than 22 is 20. So a 243 can come out, an r to the 20th power can come out, and a lonely r squared has to stay inside. Alright, let me break up my root sign now. The fifth root of 243, as we saw, is 3. The fifth root of r to the 20th power. Remember our little trick? Take your exponent here, divide by your index to get the root. R to the 20 over fifth power is r to the fourth power, times what remains inside is the fifth root of r squared. So there's my answer in simplified root form, or simplified radical form. Informally, you take out everything you can from under the root sign to write it equivalently. Alright, so that concludes section 7.3, simplifying combining rational expressions. That is all.